All right. Here we have Gauss's law problem. We've got a sphere, 0.1 meter in radius. It's got a charge of 5 picocoulombs. And that picocoulombs is evenly distributed throughout the whole sphere. Okay? So, how do we solve this problem? Well, how do we solve for the electric field both inside and outside the sphere? Now we know from Gauss's law that epsilon naught times the flux is equal to the charge enclosed by the Gaussian surface. Now, flux is equal to the area integral or the surface integral of E dot dA. Now, since E dot dA, we want something where E, electric field at every side, is either 90 degrees or 0 degrees at an angle to the electric field. Now, from a sphere, we know the electric field is going to be pointing out in all directions, right? Has to. No other way for it to go. Has to point out all directions. Well, or it could point straight in if it was negative, but in this case it's positive, so it's going to point out from all directions. So because we know that, what is the appropriate shape we want to use? We want to use a spherical shell. And the reason for that is that everywhere around it's going to be pointing at a 90-degree angle to the surface, which is what we want. Okay? So, we then slide it over here and we have inside, for the inside. So this is while we're still inside the shell, or we're inside the sphere. Okay, this is actually the harder part, so we're going to do it first. Again, we know epsilon naught times flux equals Q enclosed. Now, the flux is fairly easy to figure out. Okay, flux is going to be E dot dA, where this is the surface area. Now, what's the surface area of a shell? We're using a shell, a spherical shell, so the surface area is going to be 4 pi r squared. And because E doesn't depend on dA, because we've made it so that it's a shell, so the electric field is the same everywhere, it's going to be times, okay, times E. Nothing funky there, just times E. We can get rid of the integral, the whole thing, because we basically integrated by multiplying by the area. And then, of course, because of the dot product, it's times cosine of theta, or cosine of 0 degrees, okay, which is perfect, what we wanted. And that's equal to Q enclosed. Okay? Fantastic. Now we need to figure out what Q enclosed is. For this, we're going to use a volume ratio. Because this is evenly distributed, okay, we can figure out that the volume of, if we want to have a chunk of it, like say we want 1/5 of this, we take 1/5 the charge. So we can figure out the ratio of how much volume we want to how much we total. We can then multiply that by the total charge, and that'll give us the charge enclosed. Okay, so we're going to stick with this epsilon naught 4 pi r squared E equals 4/3 pi r cubed, which is the area of our shell, which is the volume of our shell, the chunk of the thing that we are at. Okay, so if we're taking just this, okay, inside there, over 4/3 pi times 0.1 cubed. That's the total volume. All of that times 5 picocoulombs. Okay, we get some canceling going on there. The r squared canceled, and we should get that E is equal to r over epsilon naught times 4 pi, that comes from over there, times 0.1, all times 5 picocoulombs. Okay? And this should come out to 0.1 to the third. And this should come out to be 44.9 R. And that is the electric field inside the shell. It increases, so basically what's happening is it increases linearly as we move towards it. Alright, now we're going to go to outside. I'm going to have to erase here. Apologies for that, but you can pause it, can't you? Okay, we're going to go outside. Outside is easier because what doesn't change? We know that the Q enclosed isn't going to change. So we have, again, epsilon naught times the flux equals Q enclosed. So now Q enclosed is just 5 picocoulombs, while the other side is the same as it was before. Okay, again we have 4 pi r squared times E. Okay, here's pretty simple. We solve for E. We get E is equal to 0.0449 over r squared, and we have our value. Now the interesting test to see if these are right is, are they continuous? Is these function continuous? So at radius of 0.1, when we switch from inside to outside, are they the same? So you recall that happens at r equals 0.1. So 0.449 over 0.1 squared, that should come up with being 4.49. That's outside. From the inside, the limit we have E equals 44.9 times 0.1, which is also 4.49, which tells us that, again, the function is contiguous, which is what we would expect to see. Okay, no matter which way you're coming from, we should see that the electric field at this edge of the sphere is 4.49 newtons per coulomb squared, or per coulomb.